Hello, nephrology colleagues. Good day to you that visit from USA and good afternoon to all our European participants. My name is Peter Stemmikel. I work at the nephrology department at the Karolinska Institute in Stockholm, Sweden. So welcome to the Hemodialysis Spotlight webinar series. This is a new series that aims to investigate new medical information available on hemodialysis. And I'd like to thank all of you for participating in this event. All attendee lines will be muted upon entry to the webinar and remain muted throughout the webinar. And please submit your questions via the Q&A panel. You may enter questions at any time during the program. We will start today with an 8-article series from a recent supplement at Clinical Kidney Journal, The Duality of Dialysis Membranes, Their Attributes and Ramifications. This supplement covers basic scientific and technical information with regards to dialyzer membranes as well as its clinical reflections and discussing some unresolved issues. Today, we will start the series with Dr. Faith Kirselli presenting the scientific principles and technological determinants of hemodialysis membranes. This will be a comprehensive introduction into the subsequent presentations of this series. Fatih Kirselli is Vice President for Medical Information at Fresenius Medical Care. He's a nephrologist by background, has received his medical degree from Hacettepe University in Turkey, and he was awarded with an associate professor degree in 2012. Dr. Kirselli has over 65 publications in peer-reviewed journals on a broad spectrum of topics related to hemodialysis. Fatih, please start your presentation.
Thank you, Professor Stanwinkel. I would thank you for this nice introduction. I would like to start first by thanking the audience today for joining. And without further delay, I'm happy to introduce to you the first article from the Clinical Kidney Journal supplement, where I will start by summarizing the scientific and technological determinants of hemodialysis membranes. This article is authored by Sudhir Bowery and Charles Chazot. You can reach all of these articles from the Clinical Kidney Journal link, which will be shared in the chat section of this webinar. Also, for some parts of my presentation, I use parts from the book Understanding Membranes and Dialyzers by PAPS Publishing. Before I start, I also would like to disclose, as Professor Stanwinkel addressed, I work as a Vice President for Medical Information and Education at Fresenius Medical Care. This presentation is based on the article by Sudhir Bowery and Charles Chazot, which was published in the Clinical Kidney Journal, Volume 14, Supplement 4, in December 2021. Some of the information addressed here is from the book that I addressed, authored by Uhlenbusch-Curver, Bonnie Shorn, Aileen Grassman, and Jörg Winken, which was published by PAPS Science Publishers, the first edition, April 2004. The figures are used with permission from this book. Okay, so to start with, I think to understand dialyzers and membranes, we need to start with the natural kidney and the ultimate goal that we are trying to achieve, which is mimicking the functions of the natural kidney membrane to replace the failing kidney functions. So how does a natural kidney glomerular membrane function so that we can compare it to the dialyzers that we are using in clinical practice? There are several membranous layers involved. Beginning from the capillary side that you see on the figure of the glomerulus, which brings in the blood for detoxification. The first separation barrier is the gap, or what we call as fenestrations, between the endothelial cells, cell monolayers of the vascular tissue. This is followed by three next layers, which is non-cellular matrix that constitutes the glomerular basement membrane. These are lamina rara externa, which is adjacent to the endothelial cells of capillary, lamina densa, which is in the middle, and lamina externa adjacent to the Bowman space. Lamina externa of the glomerular basement membrane is wrapped by podocytes from the visceral epithelial lining of Bowman's capsule via their network of pseudopodial protrusions. The adjoining pseudopodia or food-like processes have numerous filtration slits, which we know as slit pores between them. A thin diaphragm between the slits acts as a final filtration barrier before the fluid enters the glomerular space. So this is just a high-level description of what is happening in a natural membrane, how the filtration is occurring, and it is flowless in many cases. Filtration is the key element for getting rid of excess water and end products, as well as toxic solutes, by allowing them to diffuse or by pressure across the membrane. For filtration to occur, endothelial fenestrations with pores between 70 to 100 nanometers retain blood cells, but they permit the passage of various plasma proteins, solutes, and fluids. The three layers of the glomerular basement membrane prevent access of larger proteins, including albumin, by a combination of charge and size restriction to the lumen space, which is also the main site of restriction of water flow. The interdigitating slits between the pseudopodia of podocytes play an active role in preventing plasma proteins from entering the urinary ultrafiltrate by providing the third restrictive barrier. In a healthy kidney, this is flawless, and as you see, there are many measures not to lose beneficial substances. But we know that kidneys don't always stay healthy, and at some point, some nephrons may be lost, and we might observe a decline in filtration. Some additional notes regarding the function of natural kidney membrane are the formation of glomerular ultrafiltrate is dependent on the interplay between the glomerular pressures and flows, but also the intrinsic perm selectivity properties of the glomerular capillary wall. These intrinsic permeability properties serve to exclude macromolecules from the urinary space based on size as well as net molecular charge discrimination. So size as well as the charge of the molecule is critical. Any substance that can pass through the thin innermost separating region, which is called the skin layer and has a size of less than 50 nanometers, is able to pass through the rest of the membrane wall. The glomerulus is also key to producing the primary urine by filtering blood and retaining larger proteins, including serum albumin, as I addressed. Proteins with a molecular weight below 60 kilodaltons usually pass freely through the glomerular basement membrane and are actively absorbed within the tubular system. With the dialysis membranes, this is one property that can be modified, but if the membrane mean pore size is larger than that of albumin or the other beneficial substances, it will leak out into the dialysate, and there won't be a controlled or highly selective removal of individual proteins. So there won't be a reabsorption step, and this is not practically possible. And also, this is not something that we may prefer. So that is our miraculous kidney. What about artificial membranes? Artificial membranes are also in a way miraculous because they help us to treat our patients. And we know that today we have good outcomes, maybe not the best, but we have good outcomes when we are treating our patients. We know that throughout our history, we as humans were quite successful in introducing new technologies and improving our patient care. But I want to emphasize some key points about the difference between the natural and the artificial kidneys before I go into how we came to the technology today. So the role of the dialysis membrane is also to filter or clean human blood, like the natural kidney. but is artificial or man-made. Man-made membranes bear little resemblance to biological membranes in terms of either topography, complexity, or in their mode of action. And it doesn't replace kidney functions, it only tries to substitute. Okay, so this was some essential information about the natural kidney and the comparison or the difference between the natural kidney and the artificial membranes. To understand today dialyzers better as well as the membranes, I believe looking from a historical perspective gives us insights into this long journey to have better dialyzers as well as membranes. Since the mid-19th century, dialysis came to the focus of renal scientists trying to implement new techniques for uremia. Dialysis is actually not a word unique to nephrology community, and it has been and is still used in many different settings outside the nephrology world. There is, of course, a lot of research and substantial improvements done later on the technology of dialyzers. I will try to address some of them, the hallmark results briefly. The concept of dialysis to clean toxins from the blood was first reported by Thomas Graham in 1854 using a bell-shaped bulb dialyzer from an ox bladder. One of the other early dialyzers is the vivid diffusion machine that you see here in the slide, which was created by Abel, Rowntree, and Turner. They carried out their research in animals, directing their blood outside the body and through tubes of semi-permeable membranes made from colloidon, a material based on cellulose. We don't know if it was used in kidney replacement therapies, but most likely not. The researchers were also aware of the bioincompatibility leading to coagulation and used Hiridin as the anticoagulant. Next in history was Georg Haas. He performed his first treatments in humans. Before it was more tested in animals. Haas is especially important because he tested in humans and in 1924. So that is almost like 100 years ago. As you can see from the setup, it must have been a cumbersome process. Haas used a self-developed cabin system consisting of 16 colloidal hoses in 8 glass containers, which each were 160 centimeters long, but it functioned technically safely. The total treatment time was limited to 15 minutes only in the first patient, then 30 minutes in the second patient. However, with that time's technology, the outcome was not as hypothesized by Haas for the first 6 treatments, and all patients died. This was despite a clinical improvement with regards to uraemic symptoms in these patients. But Haas has a special place in history of hemodialysis because he successfully carried out the world's first blood washing, as he called it, outside the body. Today, we call it extracorporeal hemodialysis. Haas also noted himself that when overhydrated, he could draw fluid from the blood plasma and subsequently from the body tissues, especially the lungs, if he increased the blood side pressure in the dialysis machine over that in the rinsing solution. In doing so, he actually discovered and used hemodialysis by means of ultrafiltration. Haas dialyzer, which also used a colloidon or nitrocellulose membrane, was built in a variety of models, sizes, and used Hiridin as the anticoagulant. In 1925, he published the description of the procedure in the Clinical Weekly. Today, 95% of all dialysis patients are treated with this method, and it's also the standard procedure worldwide. The tube kidney used by him was actually the first artificial organ used in humans in the history of medicine. Hiridan was problematic because it was not biocompatible, which today we know much better. It wasn't creating the expected inhibition of bioincompatibility, and there were massive complications reported, mainly from allergic reactions because it wasn't adequately purified, and the origin species was very distant from the human genome. In the end, Haas decided to switch to heparin, which caused substantially fewer complications than Hiridan, even when it was insufficiently purified. And heparin could also be produced in larger quantities. Following the development of better purification methods in 1937, heparin was actually adopted as the necessary anticoagulant, and we still use it today. However, Haas was criticized that he could not bring a cure to patients with dialysis, but just a temporary improvement. This opinion was then to be understood out of time. In 1945, Wilhelm Kolff from the Netherlands made the breakthrough that eluded Haas. Kolff used a rotating drum kidney that he developed to perform a week-long dialysis treatment on a 67-year-old patient who was admitted to the hospital with acute kidney failure. The patient was subsequently discharged with normal kidney function. At this stage, I would like to draw your attention to the large size of tubings, which, as you can see, is between 10 to 20 meters, which was most probably not really practical. Also around the same time, Alwal came up with a vertical stationary drum dialyzer, which removed excess fluid by applying negative pressure. So now, after having at least some outcomes with normal kidney functions, the intentions to deal with ultrafiltration is increasing. Examples of the Kolff rotating drum kidney crossed the Atlantic and arrived at the Peter Brent Brigham Hospital in Boston, where they underwent a significant technical improvement. The modified machines became known as the Kolff-Brigham artificial kidney, and between 1954 and 1962, they were shipped from Boston to 22 hospitals worldwide. Now we also started seeing the application of these artificial kidneys also in different settings in different countries. Kolff was a pioneer along with other scientists to improve the efficiency of dialyzers. By proving that uraemic patients could be successfully treated using artificial kidney, Kolff later also sparked a flurry of activities around the world to develop improved and more effective dialyzers. The parallel plate dialyzer evolved as the most significant development of this period. Rather than pumping the blood through membranous tubes, this dialyzer directed the flow of the dialysis solution and blood through alternating layers of membranous material. Alwal later also described a modified dialyzer that could perform the necessary combination of dialysis and ultrafiltration better than the original Kolff kidney. This membrane was made of cellophane, but could endure higher pressures because of its positioning, as well as allowing the application of different pressure ratios. This was a significant improvement into ultrafiltration control. There were further developments until the 70s when Gambro first introduced its first mass-produced for commercial use dialyzers. This was actually preceded by a dialyzer developed from cellulose acetate, which was more efficient in terms of waste and water removal and was a basis for the standard dialyzers today. And after almost more than 100 years from the works of Graham, Fresenius introduced polysulfone dialyzers and hollow fibers for commercial use, which are today the most used dialyzer membrane type. Today, the key functional determinants of dialysis membranes have been identified in both in terms of their potential to remove uraemic retention solutes, termed as uraemic toxins, as well as the subsidiary criteria, that they must additionally fulfill to avoid undesirable patient reactions or to ensure patient safety. The production of hundreds of millions of kilometers of hollow fiber membranes is truly a technological achievement, particularly in ensuring that the fiber dimensions of the wall thickness and inner lumen diameter and control porosity, all vital to dialysis core solid removal or detoxification function, are consistently maintained for every centimeter length of the fragile fibers. Also today, we have expanded our treatment options by using dialysis in two forms, as peritoneal dialysis and hemodialysis. Before I move on to talk about how we achieve those, I want to also address the difference between these two dialysis modalities. This is mainly to address that the glomerular filtration barrier of the natural kidney and the peritoneal membrane, though both biological, have distinctly differing structure, functional relationships, and size selectivity. The natural kidney is an anatomical unit whose function is to remove waste and excess substances from the blood, producing the urine. The peritoneum is a membrane lining the abdominal cavity to support organs within it and has no physiological waste removal function. But its semi-permeable nature and microvasculature has been harnessed for dialysis in end-stage kidney failure patients. Both hemodialysis and peritoneal dialysis achieve similar overall objectives in terms of cleansing the blood of kidney failure patients by using diffusion and convection, yet each involves different patient considerations and results in variable clinical outcomes over time, and is particularly apparent when patients are switched from one modality to the other. Having talked about the natural kidney and innovations in dialysis, now I would like to take you to a journey of a dialysis membrane. Let's have a look at how an artificial membrane is produced. But let's first start with some essentials. Manufacturing of dialysis membranes is intricately linked to the spinning of yarn, which is thread made of natural or synthetic fibers for use in weaving of textiles, curtains, carpets, etc. In fact, until recently, one of the mostly frequent used hollow fiber dialysis membranes, which is cuprophane, was developed and produced in the 70s by one of the world's leading manufacturers of fibers for clothing, household fabrics, and industrial application, that is Enka in Germany. However, yarn is a solid tubular structure, and membranes for kidney replacement therapies necessitated the creation of a hollow circular space, a bore or lumen, within the thread for blood to flow through, and surrounded by a semi-permeable structure for selective transport. As hollow fibers are self-supporting structure, their dimensions, so the wall thickness relative to the lumen diameter, are crucial for stability. The production of membranes involves four critical steps. The first one is the conversion of solid polymer material, either available in nature or synthesized in the laboratory, into minute pipe-like structures, that is the fiber formation, creation of a defined structural attributes that permit semi-selective separation of biological entities having a broad size range, so that is about the membrane structure. The chemical composition of the materials selected must be such that there is minimal unfavorable interaction with a unique tissue that serves every organ and cell of the human body, blood, which is biocompatibility, and application of defined and stringent quality and safety criteria is needed. So after this production step, what about the quality parameters that we are using or we are considering? There are 5 main membrane quality outcome parameters that should be considered when developing a dialyzer membrane. The choice of the material used, the manufacturing conditions, resultant morphology, dimensions of the tubular membrane, and also the surface physicochemical properties. Yes, all these parameters are critical for developing dialyzer membranes. But one important thing in dialyzer production that it's a matter of balance between all parameters in the equation, which I will show you shortly. At the end of the process, how you design the production will determine the outcome. Production of dialyzers is a complex, lengthy process and involves many stages. Here, I'll start with stage 1. It's not only about the membrane, but I should address that it's a part of a larger ecosystem, which also includes housing, the plastic cover, and even the packaging has its own details. The first stage that you see here is about preparing a homogeneous solution, which is generally a polymer dissolved in a solvent. This casting solution normally comprises not just one polymer, as usually copolymers are required for certain membrane applications. For the manufacture of most dialysis membranes, polyvinyl pyridine, PVP, is used as a copolymer. The elements used here are very critical and will define the balance also between hydrophilicity and hydrophobicity. Today, in many dialyzer membranes, PVP is used as a copolymer. This may be one of the most important steps in the whole production. The reason for this is that PVP serves not only as a pore-forming agent to obtain an open, interconnected porous membrane structure, but also to provide a membrane structure with an optimal hydrophobic and hydrophilic balance, which is important for biocompatibility. Both of these are critical for the interaction between the membrane and the blood. Phase separation, or also address phase inversion, and I will address the difference, is the basic principle of membrane formation, whereby a polymer is transformed in a controlled way from a liquid to a solid state. Phase inversion is sometimes used, phase inversion is sometimes used interchangeably with phase separation, but inversion is more a physical phenomena whereby a polymer dissolved in a continuous phase solvent system, for example, a solution, inverts into a solid macromolecular network in which the polymer becomes the continuous phase. The process of solidification is usually initiated by the transition from one liquid state into 2 liquid states, and this is called liquid-liquid demixing. Phase separation is performed by removing the solvent from this liquid polymer solution by adding a non-solvent, leaving a porous solid scaffolding. The aim is to create a desired membrane structure that is suitable for a specific separation application and achieved by selecting appropriate polymers and controlling of various conditions of the process. Most membranes that are used in kidney replacements are based on a ternary system, a ternary phase separation system, for example, involving 3 components. So a polymer, a solvent, and a non-solvent, represented as an interconnected triangle or triad. Let me explain the interconnected triad. I know it might be kind of difficult, but I will also summarize the concept at the end. The exact location on the polymer-solvent axis indicates the composition of the solution. For example, the relative amounts of polymer and solvent. The corners of the triad represent the pure, so 100% component. At any point on one side of the triangle represents a mixture of the 2 components on the axis, and any point within the triangle denotes a mixture of the 3 components. All-phase inversion processes are based on the same thermodynamic principles, and the starting point in all cases is a thermodynamically stable solution that is then subjected to demixing, as I addressed in the previous slide. The boundary of the stable-unstable region is represented by the binodal curve denoting the condition at which any two phases may coexist to initiate the formation of a sponge-like porous structure. Variable membrane structures can be derived from either a single starting or polymer casting solution or from different starting compositions. The next process is spinning. Spinneret is another essential part in the creation of a fiber. There are three main methods used. Wet spinning is the most common. In wet spinning, a polymer, as you see on the left, a polymer solution is pumped through an orifice, and a filament is continuously drawn and simultaneously solidified in a non-solvent bath where demixing occurs because of exchange of solvent and the non-solvent. Between the spinneret and the non-solvent bath, there is an air gap where membrane formation starts. There are two general approaches regarding the structure, tailoring the structure and porosity of the dialysis membranes by selecting a single polymer solvent composition, which you see here with the red dot for the initial spinning solution, for example, along the polymer solvent axis and different thermodynamic conditions or pathways during the spinning processes, which you see as A, B, C, D here. The desired membrane structure and a solid removal characteristics is achieved. These could range from a fully sponge-like structure that you see with D, or to less desirable finger-like or vacuole shaped open spaces. The other approach is that different membrane structures having distinct solid removal capacities can also be derived by selecting variable starting solutions, for example, a different polymer solvent composition, which is indicated with open red circles from 1 to 4, and applying appropriate thermodynamic conditions for each pathway. This allows to derive membranes that are more polymer-rich on the polymer solvent axis, or those where there's higher solvent content and thus less polymer, resulting in either denser or more porous membrane structure, which you see with 1 here. So this is the whole picture that you see here. Making a membrane is a sophisticated process, and after the precipitation, there is a fastening, washing, drying, undulation. And also in some of the countries or in some places, reprocessing and reuse can also be applied later on. And after the undulation step, there is also a binding step. So this is more putting them into the dialyzers that we see. So this is stage 3 of the dialyzer production. The key membrane aspects that are important for HD therapy is the choice of the polymer. It defines the personality of the dialyzers. And today, for example, we call the membranes as polysulfone membranes. The choice and the concentrations of the copolymer is important because this defines the pore making capacity and also the biocompatibility profile of a membrane. Membrane spinning conditions and parameters selected during the condition will change the outcome of a dialyzer. So all these points has to be managed and everything should be in a balance. We should also not forget that a dialyzer membrane has its own ecosystem. And in addition to managing chemical aspects, physical attributes are also critical. For example, the spinneret dimensions, the speed, the temperature, the viscosity, humidity, pressure, residence time with air. All these are important, and these will define the 5 important properties of a dialyzer: the performance, biocompatibility, cytotoxicity, sterilization, and endotoxin retention, and I will come to that later. Now let's have a look at different parts of dialyzer and a membrane. Let's look at the wall first to have further insights into different parts of a membrane. The wall is the most critical elements for clearance, as we know. The thicker it is, the slower the movement of molecules through the wall will be, and so the clearance of mid and large molecules may be impacted. There are two types of membranes with regards to wall characteristics. The first one is the symmetric membranes, which you see the morphology from the inner to the outer wall is uniform in terms of pore size, distribution, and porosity. The other option is the other membrane type is the asymmetric membranes, where the inner region of the membrane has a thin separating region of high polymer density, and the remaining membrane wall is a more porous, sponge-like structure with less polymer. And this can be also found in different membrane types as well. Historically, due to instability, wall thickness was around 300 microns. Today, it has come down even to 10 microns for some dialyzers. The wall of a membrane will also be the barrier between the two sides, the blood and the dialysate. We should not forget that it's a bidirectional flow, and substances other than those intended may enter the patient's bloodstream via the outer wall, where it's exposed to dialysate. Bicarbonate in dialysate may also create an environment for bacteria. Endotoxins are transported by diffusion, backfiltration, or during direct infusion of substitution fluid, which is prepared from dialysis fluid into the blood circuit during convective modalities, if not approached appropriately. This is important because it elicits adverse reactions, which in extreme cases could be life-threatening. Today, we use membranes that have a higher endotoxin retention capacity, for example, polysulfone membranes, and thus a better prevention of such an influx. And also some other membrane types have this function as well. And also there are new approaches to purify water with high standards today, which decreases this problem further. For the molecule, why pore size is important now, I would also like to look at the pore size. Pore can be found in two types. So with cellulosic membranes that you see on the right, it's more like a fiber, like filaments, and the exchange is happening between these filaments. And in the synthetic membranes, this is what we see in textbooks and so on. The pore is important because it determines the transport or performance characteristics. The innermost layer determines the initial resistance to transport, which can be diffusive or convective, and any solute that is able to pass through based on its relative size to the mean pore size, it would enable to traverse the rest of the thickness of asymptomatic membranes. Pore define three important properties: hydraulic permeability, clearance, and sieving. And we know that these are all important. For hydraulic permeability, pore size, pore number, and the surface area will define the ultrafiltration coefficient of a dialyzer. One important note here is that the larger the pores, the higher the clearance of larger molecule hypothesis still holds true, but after a certain cutoff, the risk of losing beneficial molecules is also greater. And this is why pore size is very critical, and it defines the whole process. The other part is the lumen. It is the part of the membrane that is in direct contact with blood, and thus is highly important for hemocompatibility. the diameter of the fiber lumen affects the flow characteristic of blood within each fiber, influencing transport phenomena and hence overall performance. Decreased hollow fiber inner diameter alters pressure profiles such that maximize internal filtration results, a phenomenon that occurs together with backfiltration and which increases large solid clearance. As blood rheology is known to affect mechanisms like thrombosis within the body, the impact of fiber geometry has been studied with respect to biocompatibility. Hemocompatibility of a membrane is of importance. Contact of blood with an artificial surface of the extracorporeal circuit of kidney replacement therapies triggers several plasmatic waves and activation of platelets and leukocytes. Of the total surface area available for such interactions between blood and the materials, the membrane within the dialyzer constitutes the largest stimuli. The choice of the base polymer is believed to be the decisive factor determining the extent to which blood components are activated. However, it's not the only parameter, as the properties of the final product also define the interaction between the blood and artificial surfaces. The lumen is in direct contact with blood, and the type of copolymer and solvent used in the spinning of the fibers and the diverse spinning conditions determine the physicochemical properties of the blood contacting surface. The degree of surface hydrophobicity and hydrophilicity, surface charge and tension, as well as surface chemistry, which is about available chemical groups and roughness, for example, are all peculiar to each dialysis membrane's effect on blood component alterations. Protein absorption is also critical for improving hemocompatibility, and different parameters like nano-roughness, hydrophobicity, nanostructure, hydrophilicity, functional groups, and electronegativity of the membrane will impact protein absorption. And we know that protein absorption is also important for hemocompatibility, which is a critical issue. Which is critical for less adverse reactions and better performance. Hemocompatibility will be discussed in the upcoming webinar, so I'm not going to go into detail of that, but I would like to address that the choice of the base polymer, the type of copolymer and solvent used, and the diverse spinning conditions will have an impact on this. In the previous section, I tried to summarize the journey of a membrane, the production, and I also addressed that each element used has an impact on both technical and clinical outcomes. I also addressed the 5 critical elements for an ideal dialyzer, which are performance, which is about high removal rates of fluid and broad spectrum of small and large uraemic toxins without inadvertent loss of albumin, that highly open membranes cause. Biocompatibility, which is about limiting the effects of unavoidable interactions between the blood and the artificial surfaces of the extracorporeal circuit. Cytotoxicity, which is about preventing the leaching of substances from the membrane and also the other parts of the extracorporeal circuit components and entering tissues, causing cell reactions. Sterilization is also important, and it also is impacting the membranes, as utmost safety for patients are required without changing membrane characteristics. It is the sterilization method must be ensured that is appropriate for the treatment. The other part and the last part is the endotoxin retention. As dialysis fluids could potentially be contaminated with bacterial endotoxins causing persistent low-grade inflammation, modern dialysis membranes need to have high endotoxin retention capabilities, which is already available with some membrane types. We have also covered the membrane innovation journey until now. But how does the dialyzer landscape look like today? Today, a hollow fiber dialyzer bundle is comprised between 7 to 17,000, and this can change semi-permeable hollow fibers. Typical fibers have an internal diameter of 180 to 200 microns and a wall thickness of 30 to 40 microns, and yielding a surface area between 1 to 2.5 meters squares. Fibers may have features such as undulations to distribute dialysate flow evenly through the fiber bundle. There is also different membrane types available in the market, and I guess you are most familiar with these membrane types. But I would like to address to the hydroxyl groups, because the hydroxyl groups are important with regards to complement and cell activation. So the research is actually about how we can modify these side chains so that we can reach a more biocompatible and more efficient membrane. This is also a comprehensive list of available membrane types. Some of them are used much more compared to others, and some of them are preferred less. Recent innovations have decreased interest for some of them, mainly due to having dialyzers membranes today with much better hemo and biocompatibility profiles, as well as efficiency outcomes. In addition to what we discussed today with regards to membranes, there are also other potential points of innovation which are continuously being tested by scientists to see whether they may improve the current dialyzer landscape to achieve a symptom-free dialyzers. The header can be modified, the bundle design can be modified, the housing can be modified, and all of these are small but important innovations for a dialyzer. So to summarize, dialyzer membranes are the central processing units of a hemodialysis therapy. The materials and conditions selected for the manufacture of membrane have an impact far beyond the central function of elimination of uraemic toxins during hemodialysis. Today, the focus is more about reaching better mid and large molecular clearances and a better biocompatibility outcome, and hopefully one day symptom-free dialysis. The hemodialysis procedure entails prolonged and repeated contact of flowing blood within an extracorporeal circuit comprising different artificial surfaces and geometries. Several supplementary issues arise and need to be addressed when developing dialysis membranes with better hemocompatibility. And the choice of the materials used, the manufacturing conditions, resultant morphology, and dimensions of the tubular membranes, as well as surface physicochemical properties, they all impact the efficiency of detoxification of blood, patient well-being, side effects, and long-term clinical outcomes. An appreciation to the basic elements of hollow fiber membrane production would enable a more informed assessment of the possibilities and restraints of current extracorporeal kidney therapies. The pressing need for new or improved dialysis membranes is often voiced by clinicians. Over a period of 4 decades, several well-meaning and creative propositions were encountered, which seldom, though, reach fruition, as they fail to meet one or more of the myriad of technical, biomedical, safety, and regulatory requirements that need to be fulfilled or for a functioning medical device. And realizability of many new concepts is impeded by considerations involving investment in research and development, sustainability, and economy of scale during manufacturing processes of membranes. Before I end my talk, I would like to address again the main source of today's presentation and thank Clinical Kidney Journal for this comprehensive supplement. And now I would like to turn over to Professor Stenwinkel to begin moderating the Q&A session of the webinar. Professor Stenwinkel.
Thank you so much, Dr. Criselli, for taking us through this interesting and fascinating journey of the membrane. And you now have the opportunity to ask Dr. Criselli questions via the chat. So you please type your questions, and I will then moderate them so you can get answered directly from Dr. Criselli. Meanwhile, we are waiting for questions. I have a question for you. Considering the evolution of both membranes and dialyzers, what do you think we should expect as future innovations?
Thank you, Professor Stanwinkel, for this important question. So I think now with the current dialyzer membrane landscape, we have, or we can also talk about the dialyzers. I think we have achieved quite satisfying results with low molecular clearance. Today, many dialyzers and membranes can achieve this. I think the future will be about how we work on the how we can clean the mid and large molecules. I think that will be important, but I also think that now there is also the quality of life of our patients, and the quality of life is linked to a symptom-free dialysis. So a symptom-free dialysis might be providing a better quality of life. So I think from that perspective, biocompatibility is kind of addressed well, but I think hemocompatibility, so the interaction of the membrane with the blood, is something that we most probably will see. I think the other problem is also the coagulation. I tried to briefly touch the anticoagulation issue about the Hiridan and heparin, but we all know that today there is still we are using heparin, and we know that heparin has some side effects. Despite that, we are using it, and we still see some clotting. So I would also expect in the future some changes with regards to the membrane structure, so that it might be providing a better anticoagulation property. Also, bioengineering, there's a lot of research being done in bioengineering, and especially from the nanotechnology perspective. So I would also expect that those innovations coming from the biomechanical bioengineering parts will also influence maybe the newer dialyzers. Of course, maybe one day, hopefully, we might be having a much maybe smaller dialyzer that are more efficient. But of course, water is the most essential, is one of the most essential issues here, and that we also need to find a solution. So I'm excited. I think the membranes today are very highly good, but I think there will be better ones also coming in the future.
So I have a question about pruritus, which is a considerable problem for some dialysis patients. Do you think that membranes could play a role here? Better membranes quality could play a role in having an effect on this devastating pruritus that some patients have?
We know that pruritus is an important issue, and we also know that the exact mechanisms are not really defined. I'm not aware of the literature about the pruritus and the interaction within the dialyzer, but my comment would be that the more efficient dialysis that we would reach, then I would also expect some efficiencies with regards to pruritus. I think maybe we also have to look at before the early type membranes and compare it with today's membranes to see whether this problem of pruritus may be linked to some changes on the membrane perspective. But at the end, it's about some molecules that are causing this, and we just have to identify the exact mechanisms and to see if we are actually letting these molecules out, or can we let it? Because as I address, the pore size is important. If there is a larger molecule that might be causing it, then this might be still a struggle with regards to removing this. Then, because we will be treating pruritus, but we will also be losing many beneficial substances. And for pruritus, we know that there are also available medications that can be implemented. But as I said, the cause, I think, is still not so clear.
Okay, thank you. I have another question for you here. Regarding dialysis specifications, which parameter do you think is the most critical?
Okay, that's, I think, also an important question with regards to the clinical practice, but I think it goes into the similar direction that I previously tried to address. I think today we have these dialyzers or membranes with acceptable, let's call it, removal of low molecular clearances, and this is already assessed. We know that we are looking at the clearances, we are looking at the seeding coefficients also. But I think one of the parameters that maybe we might be focusing more on the clearances, but maybe less on the seeding coefficient. I think in today's world where we are discussing about removing mid and large molecules, it is hypothesized that seeding coefficient might be more important with regards to that. So I think these parameters have to be looked from both perspectives. Also, I think the patient is important, what we are trying to really achieve with that patient, because every patient might be having a different problem and we might be modifying it. I think one of the other parameters that we might look is this biocompatibility parameters, or maybe in the future quality of life parameters, which might be also indicated. But for this period, I think looking more into maybe introducing this biocompatibility parameters might also be something that might give us a better perspective. But I also know that today, mainly the information that you reach will be about the clearance, the seeding coefficient, and the general characteristics. But I would strongly urge, if it's not included in the practice, to also have a look at the seeding coefficients.
Okay, thank you so much, Dr. Kyseli. It's been a fascinating,
Professor
fascinating journey, and I'd like to thank all of you out there in the audience for participating. And I really hope you enjoyed this first meeting in a series of 8. I'd like to remind you that the next Hemodialysis Spotlight webinar will be aired on May 10th. And then we start at 1600 Central European time, and that will be 10 o'clock a.m. Eastern time, US. And that will be Dr. Chow Tao that will discuss on the membrane perspective of uraemic toxins, and which one should or can be removed and how much. And please also plan to attend the meeting June 7th. And then it's Stefano Stewart will talk about choices in hemodialysis, variants, personalized therapy, and applications of evidence-based medicine. And with this, I'd like to thank you for participating, and for all of you that are in Europe, I would say good evening. And those of you that are in the States, I wish you an enjoyable rest of your working day, and I hope to see you all next time, May 10th. Bye-bye.